Hello, I'm Seema and welcome to part 34 of the chapter Equilibrium. In this video, I'm going to tell you about the ionization constant of weak bases. In the previous three videos, I discussed the ionization constant of weak acids and then we did a few solved examples of the NCERT textbook in the next two videos, that is 32 and 33. In this video, we are just moving on with the same concept, only this time instead of finding out the ionization constant of a weak acid, we find out the ionization constant of a weak base. What is a base? According to Arrhenius, anything that releases OH negative ions in water is a base. And according to the Lewis-Bronsted definition, anything that accepts a proton is a base too. So here we take MOH. It's a metallic hydroxide generally. Any metallic hydroxide which releases OH negative ions in water would act as a base. And if it is a weak base, it would establish an equilibrium. So this is a weak base, a metallic hydroxide, which releases M positive and OH negative in water. Or it dissociates in water to give you M positive and OH negative. Just as we did for weak acids, we have the initial concentration is taken as C, and initially when you added MOH to water, there was no M positive and OH negative. So their initial concentrations were zero. If we assume that the degree of dissociation is alpha, then alpha of C dissociated. Let us assume that alpha of C dissociated, and if it dissociated, this amount C alpha out of whatever C MOH was, that much of it reacted and resulted in the formation of M positive and OH negative. If you have 1 mole of MOH, you get 1 mole of M positive and 1 mole of OH negative. So if C alpha of MOH reacted, if this is the concentration that reacted, then the concentration of M positive and OH negative formed would be the same according to the stoichiometry of the chemical equation. So if C alpha reacts, then you add C alpha is formed and C alpha is formed here. So when equilibrium is established, what is the concentration or what are the concentrations of the different species in the equilibrium mixture? The concentration of the reactant MOH, that is the base, would be C minus C alpha, because what is left would be, initially you had C, out of which C alpha reacted. So what you are left with is C minus C alpha, and the concentrations of both the products would be C alpha and C alpha. And the rest of the process is very similar to what we did for acids, for weak acids. Now, before I come to that step, let us just revise or give you examples of a few weak bases. Ammonia is commonly known as a very weak base. And all derivatives of ammonia, you usually, what are derivatives of ammonia? Where the hydrogens of ammonia, they are replaced by some other species. Those species also tend to act as weak bases. So, examples of weak bases are ammonia and its derivatives. For example, you have methylamine or methanamine, CH3NH2, which means one of the hydrogens has been replaced by a methyl group. Dimethylamine would be CH3 whole twice NH. So two of the hydrogens of ammonia have been replaced by methyl groups. Triethylamine, all the 3 hydrogens of ammonia have been replaced by methyl groups. Then you have ammonium hydroxide, a water molecule added to ammonia. Quinine, it's a biological molecule. Pyridine is a cyclic molecule, C5H5N. It has nitrogen in it. Aniline is C6H5NH2, and urea is CONH2 whole twice. These are just examples of a few weak bases. We'll go into the structures of all these when you do your organic chemistry, so I'm not going to deal with this right now. If you take an example of ammonia as a base, what happens when you add ammonia to water? It results in the formation of ammonium ion. The hydrogen of the proton is accepted from the water molecule. So in this reaction, water acts as an acid and ammonia acts as a base. It accepts the proton, forms ammonium ion, and the water results in the formation of the OH negative ion. Anyway, these were just examples of weak bases and how they dissociate in water. Let us come back to this point. You have MOH, I told you the equilibrium concentrations are now known to us. The equilibrium concentrations, if you know, you can find out the equilibrium constant. Now, the ionization constant for acids was Ka, so the dissociation constant or the ionization constant for bases would be written as Kb. So what would Kb be equal to? Kb would be the concentration of M positive into concentration of OH negative divided by concentration of the reactant, that is MOH. And again, if there was water, we ignore the water. Of course there was water, but we ignore the water because water is a liquid and it will not be in the reaction. So if you now substitute the values of these equilibrium concentrations as you have calculated them, you'll get C alpha whole square divided by C minus C alpha, right? Yeah, because C alpha is the concentration of M positive, C alpha is the concentration of OH negative too. So if you take C common here, you'll get C alpha whole square divided by C1 minus alpha. And if you cancel out one of the C's here, you'll get C, only one C will remain, and alpha square divided by 1 minus alpha. So this is the equation that you get for the equilibrium constant, right? Now, just as we calculated the pKa value for equilibrium constant for dissociation of acids, similarly, you can find out the pKb value also. What was pKa? pKa was just like you have the pH, the minus log of the hydrogen ion concentration. The same concept has been extended to find out the power or the potential of Ka, Kb. So what would pKb be? pKb would be equal to minus log of Kb, right? Just as it's just an extension of the concept of pH for the Kb value, right? Now, let me just solve two solved examples before finishing this video. Let me write down the question. I'll be back in a minute. Okay. So this is question 7.21, the solved example of your NCERT text. The question reads, the pH of 0.004 molar hydrazine solution is 9.7. You have to calculate its Kb and pKb. This is a very interesting question because it's starting from the end. We usually have the concentrations initial and something about these concentrations we know, the equilibrium concentrations, or we calculate them. Then we calculate the Kb value, then we calculate the pKb value. But here they've told you something that is not at all, that appears to be not at all there in the reaction. The reaction does not have, what is pH? pH is the hydrogen ion concentration, and that has not been given in this equation. And actually it is not there in this primary equation. If you remember, in the previous videos, or rather two videos before this, that is 34, 33, 32, maybe 31, I told you that there are two equations when you have a weak acid or a weak base. One is the weak base dissociating, and the second into water, and the other is the water molecules themselves acting as acid and base and resulting in the formation of H3O positive and OH negative, in which one water molecule acts as an acid and the other one acts as a base. And the equilibrium constant, or the ionic product of water that we call it, is 10 to the power minus 14, or 1 into 10 to the power minus 14. And whatever this equation is, usually its ionic product is greater than that of water, and therefore this becomes the primary equation, and the other equation, that is water molecules and the ionic product, where you have the ionic product of water is equal to 10 to the power minus 14, that becomes the subsidiary or the secondary equation. Now, they have given you in this question the pH, which means that it is a part of this value is in the subsidiary reaction. That the water and the water molecule, they reacted, they have got a pH of 9 point, where it has produced hydronium ion, and that has a pH of 9.7. So what is pH? According to definition, pH is the minus log of the hydrogen ion concentration, or the hydronium ion concentration, which I used interchangeably. Now, minus log of hydrogen ion concentration is given to us. What is it? It is equal to 9.7. So can we find out if minus log of hydrogen ion is 9.7, then what is H positive? It would be the anti-log of the negative value of this. So it is, since pH is the negative log of this, if you want to find out H positive would then be equal to the negative log of the pH value. So this would be, the negative anti-log, because the log is given to us. This value is a log, so it is the negative anti-log of the pH value. So you'd find this would be negative of anti-log of 9.7 would give you the value of hydrogen ion concentration. And when you find out the anti-log of this, you get the value 1.67 into 10 to the power minus 10. 1.67 into 10 to the power minus 10 is the concentration of hydrogen ion. Yes. Now we know the ionic product of water, that is H positive concentration into OH negative concentration upon H2O, where H2O is a liquid, so we ignore it. The ionic product of water is equal to 10 to the power minus 14, right? 1 into 10 to the power, or we can say 1 into 10 to the power minus 14, just to make it somewhat similar. It is 1 into 10 to the power minus 14. So we know H positive. If we have to calculate OH negative would be, OH negative concentration would be equal to 1 into 10 to the power minus 14 divided by the H positive concentration, right? And what is the H positive concentration that we've calculated? This. So this would be equal to 1 into 10 to the power minus 14 divided by 1.67 into 10 to the power minus 10. From this, you'll get the concentration of OH negative at equilibrium. Because on the whole, whatever OH negative is present, whether it is from one reaction or both the reactions, on the whole, the ionic product of water in the solution should be 10 to the power minus 14. So whatever this reaction is contributing and whatever the other reaction is contributing, the total concentration of OH negative at equilibrium would be this. And how much is that? That when you calculate it, it comes out to be equal to 5.98 into 10 to the power minus 5. 5.98 into 10 to the power minus 5 is the concentration of OH negative at equilibrium. Now, according to the balanced chemical equation, the concentration of NH2NH3 positive, that is the hydrazonium ion, and OH negative is equal. Therefore, this is also the concentration of NH2NH3 positive. So, this is also the concentration of NH2NH3 positive. And what is the question? You have to find out Kb. Now, this concentration is 5.98 into 10 to the power minus 5. And what was the molarity of hydrazine? It was 0.004 10 to the power minus 3. So this is much smaller than that. So we can ignore this concentration. If you remove this much from this amount of hydrazine, that the concentration of hydrazine almost remains the same. So we ignore this amount, because what would the concentration of hydrazine be at equilibrium? It would be 0.004 minus this value, isn't it? It would be minus this value, C minus C alpha. So this would be, this is C alpha. So it would be minus this value, but since this value is very small, we ignore it and we assume that the equilibrium concentration of hydrazine is 0.004. So taking that, if you have to calculate Kb, Kb is NH2 NH3 positive into OH negative products, the concentration of products divided by concentration of reactant, that is NH2 NH2, equilibrium concentrations. Now this is 5.98 into 10 to the power minus 5 whole square divided by, we keep this to be 0.004. We do not subtract this amount from it. We just keep it as 0.004. And when you calculate this, you get the value of Kb. And the value of Kb comes out to be equal to 8.96 into 10 to the power 8.96 into 10 to the power minus 7 is the value of Kb. And so now what would pKb be? Right? We've now found out the value of Kb. And what would pKb be? pKb would be the minus log of Kb, which is equal to minus log of, what is Kb? 8.96 into 10 to the power minus 7. And when you solve this, you find out the log of this, you'll get, this value will come out to be 6.04. Right? So that is the value of pKb. So this was question 7.21. And give me a moment, I'll now write down question 7.22. Okay, so now this is question 7.22. Let me read the question. You have to calculate the pH of the solution in which a mixture of 0.2 molar ammonium chloride and 0.1 molar ammonia are present. The pKb value of ammonia is given, which is 4.75. Now you've been given two compounds that have been mixed in water, and this mixture now has three compounds in it. It has ammonium chloride, it has ammonia, and it has water. Ammonium chloride is a salt. So we are doing ionization constant of bases right now. So the reaction here that you're interested in is the reaction of ammonia, because ammonia acts as a weak base. And you've been given the pKb value of ammonia, which means the primary reaction here is that of ammonia. So what is the primary reaction? Ammonia combines with water to produce ammonium ion plus OH negative ion. Right? Now why has ammonium chloride been thrown into the mixture? Has it been thrown in just to confuse you? Or has it been thrown in? Does it have some role in this? You know, just as we take the subsidiary reaction to be that of water and water molecule, and we take the ionic product of water to calculate the total concentration of OH negative and H positive in the equilibrium mixture. In this equilibrium mixture, the ammonium chloride salt that you have thrown into the mixture, that ammonium chloride is also going to dissociate. After all, it's an ionic compound. It is going to dissociate, and it is also going to contribute to the ammonium ions. So here, the concentration of ammonium ion is actually telling you that as soon as you threw it into the mixture, the ammonium ion is contributing its own concentration of ammonium ions. It has its own concentration of ammonium ions. So in this mixture, initially, what was the amount of ammonia we had? Let us say we had the initial concentration of ammonia is given, yes, 0.1. So initial concentration of ammonia was 0.1 molar, right? And ammonium ion initially was 0 and OH negative was also 0. But as reaction started, let us assume that X amount of ammonia dissociated. I'm not taking the degree of dissociation here. So we'll say minus X. X amount of ammonia has reacted. Therefore, what about ammonium and OH negative? X amount should be formed, right? It should be plus X. This should also be plus X. But here is the hitch. The addition of ammonium chloride, the 0.2 moles of ammonium chloride, that would be added to this mixture. 0.2 moles plus X would be the concentration of ammonium ion. Because that much, 0.2 moles is being contributed by the ammonium chloride. So at equilibrium, the concentration of ammonium ions is not going to be X, it is going to be X plus 0.2. And at equilibrium, the concentration of ammonia is going to be 0.1 minus X. Am I clear? So now we know the equilibrium concentrations of all the reactants and the products. So from this, what is the equilibrium constant? What is the equation for the equilibrium constant? Equilibrium constant for this reaction would be equal to concentration of ammonium ions into concentration of OH negative ions divided by the concentration of ammonia, which is equal to this will be 0.2 plus x into x divided by 0.1 minus x. So this is the equation that you're going to get. But the question is, our aim is to find out what x is. What is the step? The next step is that we should know x. In order to know x, we should know the value of Kb. And in order to know the value of Kb, what is given to us in the question? We've not been given Kb, we've been given pKb. And what is pKb? pKb is the negative log of Kb. So we've been given the value, the pKb value, which is equal to, K should be capital and the B should be a subscript. There's the duster. P is small, K is capital and B is a subscript. pKb value is equal to the minus log of Kb. So what would Kb be? Kb would be the antilog of minus pKb, or you could say the minus antilog of pKb. So this would be equal to antilog of minus what value? 4.75, which means it is equal to 10 to the power minus 4.75 would be Kb. And when you calculate this, what does this come out to be equal to? This comes out to be equal to 1.77 into 10 to the power minus 5. 1.77 into 10 to the power minus 5 is the value of Kb. Now this is a very small value, and here we said that Kb is equal to this. Kb is equal to 0.2 plus x into x upon 0.1 minus x, right? And Kb is how much? Is equal to 1.77 into 10 to the power minus 5, right? Now 1.77 into 10 to the power minus 5 is a very small number. The dissociation constant is very small, which means that this amount x is actually a very small quantity. And since it's a very small quantity, for these two values where you have 0.2 as the concentration, 0.2 plus x would be approximately equal to 0.2 moles. And 0.1 minus x would also be approximately equal to 0.1x. So we can simplify this by assuming these to be, this value to be equal to 0.2 and this value to be equal to 0.1. So this becomes 0.2 into x, which is outside, upon 0.1 is equal to 1.77 into 10 to the power minus 5. From this you can calculate the value of x would be 1.77 into 10 to the power minus 5 into 0.1 upon 0.2, and when you calculate this, this comes out to be equal to 0.88 into 10 to the power minus 5. Now what is x? X is the concentration of OH negative. X is the concentration of OH negative at equilibrium. So we can write OH negative concentration is equal to 0.88 into 10 to the power minus 5. What is given to us? You have to calculate the pH from this, right? You have to calculate the pH from this. OH negative concentration is this. So from the ionic product of water, you can calculate the concentration of H positive, just as we did in the previous problem. We found out the concentration of OH negative. Here we're going to find out the concentration of H positive. We know that H positive into OH negative is equal to 1 into 10 to the power minus 14. So we have OH negative here. So H positive would be equal to, since there's less space, let me just do the steps here. I'll divide the value of this value by the OH negative concentration. So divided by 0.88 into 10 to the power minus 5. And when you solve this, this comes out to be equal to 1.12 into 10 to the power minus 9. 1.12 into 10 to the power minus 9 comes out to be the concentration of H positive. And that's our question. You have to calculate the pH of the solution. So now you know the H positive ion concentration. And what is pH? pH is equal to the minus log of H positive ion concentration, which is equal to the minus log of what is the H positive concentration? 1.12 into 10 to the power minus 9. And when you find this out, the value comes out to be 8.95. The value is 8.95. So that is the pH of the solution. So with this, I end this topic. In the next video, I'm going to do the relation between Ka and Kb with you. So if you found this video helpful, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.